All right, so happy International Women's Day, everybody, and welcome to today's session of the Cardiff Analysis Seminar. Today, we're very delighted to have Jussi Behrndt from Graz, who will talk about spectral theory for Dirac operators with singular potential. So without further ado, over to you, and thank you very much.
Okay, so thank you very much for inviting me to speak in your seminar. Hello to Cardiff. Hello to all others. I noted there are a couple of people in the audience I haven't seen for a long time. So it's a pleasure to at least meet you here virtually. So, okay, let's go back to the title slides. This is about Dirac operators with singular potentials, and it is based on a couple of papers we've been writing in the last few years. This is mainly with Pavel Exner, Markus Holzmann, who's from my group here in Graz, Vladimir Lotoreichik, who moved to Prague some years ago. And there's also a joint project with Thomas Ourmieres-Bonafos and Konstantin Pankrashkin. They have now moved from Paris. Konstantin is in Oldenburg and Thomas is in Marseille. All right, so the talk consists of actually three parts. The first one is an introductory part. This is not for experts, but for general audience. And in the second and in the third part, we then focus on singular delta type interactions. And well, this is basically what we have been contributing in this context. Okay, anyway, we start very elementary. I also provide a reference here for Dirac operators and equations. We've been using the monograph of Thaler, which we found is a good general and accessible book in this context. All right, so you see Schrödinger here first, and the time-dependent Schrödinger equation, which is being used to describe the motion of an electron in an electric field. So there is, of course, the t derivative, the time derivative, the Schrödinger operator here. And in addition, you add an initial condition. Although this has been used a lot, this is an equation that does not model relativistic effects or a spin of a particle. Instead, this is done by the Dirac equation. You see Paul Dirac here and his equation, which one can motivate physically, of course. It comes via a linearization process. And yeah, you end up with this type of time-dependent Dirac equation, which then takes into account relativistic effects. There are a couple of symbols and objects in here. The Dirac matrices, so the alpha J, they are 4x4 matrices formed by the Pauli matrices, sigma 1, 2, and 3 down here. And beta is also a 4x4 matrix, which is appearing in the Dirac equation right here. We shall use abbreviation for alpha J and the partial derivatives, which I'll just write for the sum alpha dot gradient. The speed of light, c, we shall set equal to 1 in the following, and the mass of the particle is assumed to be non-negative. Okay, so the Dirac equation, if you just use a formal type of Dirac operator, can be written in the first order evolution equation, which has been done here. So if we just name this part of the time-dependent Dirac equation by AV, so here is an electric potential involved, the time-dependent Dirac equation can just be rewritten in this short, simple form. And hence you can solve it by the corresponding, let's say, unitary group. And the evolution of a state F naught is described by e to the power minus I AVT times the initial value or initial state for t non-negative. And why is that? Well, you just plug it in. Now on a formal level, if you form the time derivative of this F, well, you just take the derivative of e to the power minus I AVT. So it gives you this operator here, and you just see that this Cauchy problem is kind of solved. Anyway, this is all on a very formal level, and it leads us to, let's say, fundamental problems in operator theory and mathematical physics. So the first one is you want to ensure self-adjointness of the Dirac operator, also in order to make sense of this semigroup, for example, by the functional calculus. The operators here, they act in a vector-valued L2 space. In this case, it's C4-valued functions, so we shall just denote this space by L2 R3 to the power 4. And of course, when it comes to self-adjointness in this Hilbert space, it comes to a proper choice of the operator domain. Yeah, once you have ensured self-adjointness, the next typical question is to understand the spectral properties of this operator. Let's say, very roughly speaking, you want to describe eigenvalues, continuous spectrum, absolutely continuous spectrum, and such things. And well, what we will not talk about here too much is actually scattering theory, where you basically try to describe the time evolution of a state of the perturbed Dirac operator. So here is a potential V. In terms of time evolution of the unperturbed, the free operator, so A naught just stands for the case where there is no potential, well, when time goes to plus or minus infinity. Okay, so this is a very brief warm up. So now let's try to get a bit more precise. So in the case there is no electric field, no potential, a natural choice for the operator domain of the Dirac operator would be the Sobolev space H1. And in that case, one views A naught as, well, a linear first order differential operator in that L2 space. So I just recall here, H1 is the Sobolev space of all L2 functions which admit first order weak derivatives that again are L2. And if you choose this as domain of A naught, then at least this is a densely defined operator in L2. It will be unbounded as an operator in L2. And hence one has to be a bit careful with concepts like self-adjointness and symmetry and so on. Namely, I will recall the definitions in a moment. Symmetry and self-adjointness are different concepts. One is stronger than the other. Self-adjointness is stronger than symmetry. And yeah, one just has to be careful when forming or computing the adjoint in general. Well, when dealing with Dirac operators, I think this is a well-known standard, but very useful fact. There's a direct connection to the Laplacian. So if you form the square of A naught, you just get the Laplacian or minus Laplacian plus m squared, and well, defined on the second order Sobolev space H2. So by this relation, one also obtains an integral formula or an integral expression for the resolvent of A naught with the Green's function that can explicitly be given and has this particular form down here. Good. So if we now perturb our free Dirac operator by a potential V, typical problems in operator theory appear. So we shall regard AV as a perturbation. The perturbation term V itself is just assumed to be some linear operator in general. And in order to approach AV, we shall kind of use classical operator perturbation results. Anyway, there are a number of questions in this context. So it already starts how to understand this symbol plus in equation 1. In the case that the perturbation and the operator A naught have different domains, well, that depends, of course, very much on the choice of the V. And even if A naught itself is a self-adjoint operator, one has to put conditions on the perturbations so that AV as the perturbed operator remains or becomes self-adjoint. Spectral theory for AV will be a main question. Yeah, and the V's one is interested, let's say, in concrete applications for Dirac operators are in the simplest case just diagonal 4x4 matrices. So this is an electrostatic case. So the V is a diagonal matrix with the same entry, a real valued function on each of the 4 diagonal entries. Or there are situations in physics where one also adds a so-called Lorentz scalar potential. This is again a diagonal matrix, but beta is not the identity. Instead of it's the matrix with 1, 1 on the upper entries and -1, -1 on the lower two diagonal entries. And there one may also add a so-called anomalous magnetic potential, which will not play a role in this talk. Okay, so now I'm not sure if that is necessary at all, but let me spend a minute or two by just recalling some basic concepts from abstract operator theory about symmetric and self-adjoint operators, unbounded, of course. And it just starts with the definition of the adjoint operator. So if we have an operator S acting in a Hilbert space, it's important to assume that its domain is dense. Then the adjoint operator S star is defined by the following formula. Let's look at the domain first. The domain of the adjoint consists of all those vectors G in our Hilbert space, such that for some G prime, we have this identity for any F in the domain of S. So in that case, G prime will be set as the value or the action of S star applied to G. And that this is a meaningful definition is also based on the fact that domain of S itself is assumed to be dense. So S star in this situation will really be an operator. With this definition of the adjoint, the notions of symmetry and self-adjoint are defined as follows. So an operator is called symmetric if S is contained in its adjoint. So this inclusion is in the sense of graphs. So the graph of S is contained in the graph of S star, which means their domains are contained in each other. And if you restrict S star to the smaller domain, it acts in the same way as S. Well, and a stronger notion, and for us important, is the notion of self-adjointness, in which case S and S star actually coincide. So they have the same domains, and on the same common domain, they have the same action. All right. So when it comes to spectral theory, also resolvent growth or growth of the inverse is an important issue. So for a symmetric operator and non-real lambda, one always has a bounded inverse S minus lambda. So this is like a first order growth when lambda tends to the real line. And this estimate holds for all those elements G where it is meaningful. So all those G which are in the range of S minus lambda. So next is, if S is a closed operator, we shall define a resolvent set and spectrum as follows. We say that lambda is a point in the resolvent set if and only if S minus lambda inverse is a bounded everywhere defined operator in H. And the complement of the resolvent set is the spectrum of S. So we have just split the complex plane in the two disjoint sets, spectrum and resolvent set. And then we will further split the spectrum into eigenvalues, point spectrum, sigma p of S. These are all those lambda where S minus lambda is not invertible. Then we have continuous spectrum, which are all those lambda in the complex plane where S minus lambda is invertible, but the inverse is just defined on a dense subspace. So the range of S minus lambda is not the full space, but it is dense as indicated here. And finally, there is residual spectrum, which consists of all those lambda where S minus lambda is invertible, but the inverse is not densely defined. So with these definitions, we have decomposed the spectrum further in the three disjoint sets, point, continuous, and residual spectrum. Now, for a symmetric operator, one has certain spectral properties. Well, for a closed symmetric operator. So the points of the real line, they are either in the resolvent set of S, or they may belong to the residual spectrum. So S minus lambda inverse may be defined on just on a subspace here, where for rho of S, it is defined on all of H. But in any case, the point spectrum and the continuous spectrum for a symmetric operator is always contained in the real line. So for a self-adjoint operator, which are those we are interested in, the situation is better. So the main difference is that there is no residual spectrum. So all points of the real line are necessarily in the resolvent set. We have a bounded everywhere defined inverse, and therefore the spectrum is real. And on the real line, well, as for a symmetric operator too, there is no residual spectrum. So the spectrum of a self-adjoint operator just consists of point spectrum and continuous spectrum, all located on the real line. Then there is some further definition of spectrum here just for the self-adjoint case. We shall denote those eigenvalues which are isolated on the real line, isolated in the real spectrum, that have finite dimensional eigenspaces. These we call discrete spectrum, and the complement of the discrete spectrum inside the spectrum of S is denoted and called the essential spectrum of our self-adjoint operator S. So the essential spectrum, roughly spoken, consists of a spectrum which is really kind of representing the infinite dimensionality of the Hilbert space. So essential spectrum is spectrum that is continuous, or it may be an embedded eigenvalue, an eigenvalue within the continuous spectrum, or it can be an isolated eigenvalue, in which case it is an infinite dimensional isolated eigenvalue. Okay, now let me recall a very well-known perturbation result. This is a variant of Cato-Rellich, which is useful for Dirac operators. So suppose S is a self-adjoint operator and V is just symmetric. And we have that the domain of S is contained in the domain of the perturbation V. And we have that V is bounded with respect to S, or relatively bounded with respect to S. So in this relative bound, it's important that this constant B here in front of SF is less than 1, strictly less than 1. And in that case, the sum, which is here, of course, easy to define because the domains are contained in each other, the sum will be a self-adjoint operator. So S self-adjoint, V symmetric, but under this relative bound condition, one gets a self-adjoint S plus V. And if in addition there is some relative compactness, for example, if the domain of S equipped with the graph norm and V restricted to this Banach space, mapping into H is compact, or the same on the square of the domain of S, and with respect to the graph norm of S squared, in that case we also have invariance of the essential spectrum. So relative boundedness suffices for self-adjointness of the sum of the perturbed operator, but in order to prove invariance of the essential spectrum, one needs some form of relative compactness, relative form compactness, or a different compactness type assumption. Anyway, this version of Cato-Rellich here is useful when considering Dirac operators, which we now do once more in a, let's say, more rigorous way. So again, you see the free Dirac operator here, no potential, and yeah, it's well known. This you can just check using the Fourier transform. If you define A naught on the Sobolev space H1, then this becomes a self-adjoint operator in L2. And the spectrum of this operator consists of two half lines. There is a gap around 0, which is determined by the mass m of the particle. So this operator is not semi-bounded from below. You see the spectrum goes to minus infinity. The spectrum is, purely absolutely continuous, even one can prove, but for us it suffices to remember that this is just essential spectrum. Well, now here is at least one classical result I would like to show to you. It goes back to Cato, Jürgens-Rellich, Schminke, and there are many other contributors, but I just picked this one to give you a feeling for Dirac operators and perturbations by classical potentials. So in the Coulomb case, it is essential to have this factor on the denominator here bounded by square root 3/2. And in that case, one can verify that this perturbed Dirac operator, where we perturb now by the Coulomb potential, remains self-adjoint on the Sobolev space H1. And also its spectrum doesn't change substantially in the sense that the essential spectrum is invariant. This is, of course, Cartorellich here behind. And inside the gap of the essential spectrum, so this is a gap from minus m to m, there may appear discrete eigenvalues. And these discrete eigenvalues, they may well accumulate to m or minus m. So this is just to give you an idea of, let's say, a classical spectral situation for a Dirac operator, in that case perturbed by the Coulomb potential. So all that was kind of warm up. And now let's approach the objectives of this talk. So here we shall assume that our perturbation, our potential V, consists of the two terms. There is an electrostatic term and there is a Lorentz scalar term. And we shall assume that these functions VL and VSC are strongly localized near some hypersurface. And then actually we will treat a kind of model potential where we replace these classical potentials VL and VSC by constants. And here is a delta distribution which is supported on the hypersurface that is kind of the center of localization of this classical strongly localized potential. So, well, as a picture here, the idea is to consider potentials of this form and then actually as approximation to replace it actually by a delta potential and to do and perform a spectral theory for Dirac operators with potentials of this type. Fine. So this is the goal in a sense. And we will do that in the 3D and in the 2D case. And let me start with the 3D case because it has been investigated in more detail and also earlier than this 2D case, which is more recent. Fine. So once again, the goal is to study the spectrum and to define rigorously Dirac operators of this form. So the first part here is again the free Dirac operator, and the potential V formally is eta plus tau beta. Beta is this 4x4 matrix, which is 1, 1, minus 1, minus 1 on the diagonal. And then there is a delta distribution supported on some hypersurface. And this hypersurface actually appears as the boundary of a bounded C2 domain omega plus. Eta and tau here are assumed to be constants. One can also treat the case of variable functions eta tau, which becomes technically more involved. Here we shall stick to the case that eta tau are just real constants. The outward unit normal vector field on omega plus shall be denoted by nu. And the complement of omega plus, which is now an unbounded exterior domain, of course with the same boundary sigma, will be denoted by omega minus. And we shall also employ the notation f plus plus f minus for L2 functions, which are decomposed in a type of vector notation in their component, which is in the on omega plus and a component in omega minus. Okay. Now with these, let's say, notations and some formal integration by parts computation, one can kind of see how the operator domain should look like. And here's the essential point. So the definition of this formal object on top of that slide is given down here. Actually, as you can see, there is no distribution visible in the action of this operator. So it's just the free Dirac expression on the bounded interior domain omega plus times or plus the free Dirac expression acting on f minus on this unbounded domain omega minus. And now this whole delta distribution, delta potential is entering in boundary or transmission conditions. So f plus and f minus, they both are assumed to be in the Sobolev space H1 on the respective domain. And the jump or transmission condition is here at the bottom line. So what we do, very roughly speaking, is we compare the jump of the traces of f plus and f minus on that hypersurface with their well, with their medium or middle value or something like that. And eta and tau will enter here. So this condition looks kind of artificial, but it actually can be justified by an integration by parts. So this is a condition you end up if you want to model this type of potential in a rigorous way. And in fact, if the constants eta and tau both are zero, in which case you don't you don't have a perturbation here. In that case, this boundary condition reduces to a smoothness condition. So this whole term here is vanishing. And that means F plus and F minus have the same trace, which leads to the Sobolev space H1 as domain of this operator A00. So one obtains the free Dirac operator in that special case. All right. So let's do spectral theory for these operators A, eta, tau. And one has to distinguish two cases. The so-called non-critical case is the case where the constants eta and tau are chosen such that eta squared minus tau squared is not equal to 4. In that case, one verifies that this Dirac operator from the previous slide is in fact self-adjoint, and one can give an expression for its resolvent in terms of the resolvent of the free Dirac operator and some perturbation term. With this perturbation term, one can compute. It is basically built of integral operators where the integral kernel is the Green's function of the free Dirac operator. And now one has to be careful. So phi star takes you from the L2 space on the Euclidean space to the L2 space on the surface. C lambda is some hypersingular integral operator. You could view it as a Q function or Weil function or M function in an abstract setting. This is an integral operator on the L2 space on the hypersurface. And now phi lambda again takes you back from the hypersurface to the Euclidean space with an integral operator of this form. So they formally look all the same, but one has to be careful where X and the integration takes place. Okay, this gives you a resolvent formula, and this is also an approach to the spectral theory because we can now regard the resolvent of the singular perturbed Dirac operator as a perturbation of the resolvent of the free Dirac. And that leads to some results in terms of the spectrum. So in this non-critical case, which we consider here, the essential spectrum remains invariant. So there is a compactness condition, or there is compactness of the resolvent differences behind because the hypersurface is bounded. Even more, there may appear spectrum in the gap, but just finitely many eigenvalues. All these eigenvalues will be discrete eigenvalues, so eigenvalues of finite multiplicity, but just finitely many in any case. And one can even prove that under certain smallness conditions for eta plus tau and eta minus tau, there is no discrete spectrum in the gap at all. So the gap remains empty. Good. Now there are all kinds of, let's say, small symmetry type results. Under certain conditions, like eta squared not equal to tau squared, one can prove some symmetry properties of eigenvalues. So lambda is in the point spectrum of A eta tau if and only if lambda is in this point spectrum of this A with these complicated interaction strengths. That leads to even multiplicity of eigenvalues. Another symmetry property, lambda is in the point spectrum of A eta tau if and only if minus lambda is in the point spectrum of A minus eta tau. Such type of things can be obtained by considering the resolvent difference in Krein's formula and properties of the integral operators. A case that has been studied mainly in the literature is the purely electrostatic case. So there is no Lorentz scalar term in the interaction, which means tau is equal to 0. In this situation, things simplify a little bit. Now, in order to be non-critical, tau is 0, so eta should be not equal to plus or minus 2. In that case, the resolvent formula simplifies a little bit in its expression. Of course, the essential spectrum remains the same. There is just finitely many eigenvalues in the gap as we had before. There is a kind of Biermann-Schwinger principle where you compare the singularities of this perturbation term inside on the surface with the singularities of the resolvent. So you can characterize eigenvalues in the gap by the eigenvalue or by the properties of this Q or M function C lambda. Well, again, now the condition is a little bit simpler. For certain etas, there is no discrete spectrum. The gap remains empty. Some symmetry properties, which maybe I will not all now discuss again in detail.
Sorry, Jussi, can I ask a question?
Of course.
Are you in R3 here?
Yes.
Okay. And why is it important that you're in R3 and not, say, in R2? Where does the dimension come into it?
Not so much, actually. This is in the 2D case, we shall have even some more specific observations I will show you in a few minutes. The 3D case is just what we have been treating first, because that has been treated in the literature mostly. But the dimension itself, it doesn't enter here very much. So,
right. So, for example, the Crane resolvent identity, which is on the screen just now,
yes,
that would remain the same. Just maybe the formula for phi lambda would change a little bit.
Yes, that would hold actually in any dimension if one would consider Dirac operators in n-dimensional space. Yes.
Okay. Thanks.
So this is not very much depending on the dimension. That's actually true. Thank you. This is good comment.
Sorry to jump in. We have another question in the chat. So Frank Rosler asks,
yeah.
Is there a physical meaning for eta squared minus tau squared equals 4?
No, this is a good question. No, no, we have been wondering about that. So this is, for the moment, this is a kind of technical condition. Yeah? We treat this non-critical case. We call it non-critical because the situation is kind of convenient and easy to treat. In the case where eta squared minus tau squared is equal to 4, one loses a certain compactness of a certain operator, and that will show us some different results just on the next slide, I think. So this is, for the moment, a purely technical condition. We have no physical interpretation for it. But things change if we now move to the so-called critical case. Yeah, so let's continue. So what is the situation if eta squared minus tau squared is equal to 4? And in this critical case, it's not fully understood, actually. So let me just look at the particular situation where there is no Lorentz scalar perturbation term, but just the electrostatic term. So it means we consider the case eta plus minus, eta is equal to plus or minus 2. Well, of course, you can define the operator in exactly the same way, which would reduce here now to this transmission condition. The index should be plus minus 2, 0, actually. But the properties are different. So again, integration by parts shows that this is a symmetric operator in L2, but it's not self-adjoint on that domain. And one actually has to take the closure. So it is essentially self-adjoint. The closure, therefore, is self-adjoint. One has the same type of transmission conditions for the domain of the self-adjoint closure, with the little difference that the functions become less regular, and this trace or this transmission condition has to be read in h minus a half on the surface, whereas the condition above here and before was always on the L2 space on the surface. So now we are getting a bit more singular. This is a small difference. And the main difference is the following. So the essential spectrum, the half axis from we had before, they are still contained in the essential spectrum. This is certainly the case, but there can be more essential spectrum. So in the gap, you may find essential spectrum. We don't have a full general result for this case, but we have, well, kind of examples or results where under certain geometric conditions on the hypersurface, there appears essential spectrum. And the simplest one is actually that sigma contains a flat part. So if this hypersurface just contains a flat part, can be small, but of course of positive measure, then actually 0 becomes a point in the essential spectrum of this operator. So in this critical case, the spectrum in the gap is different from a qualitative nature. There may appear essential spectrum. Okay. So here are some references for 3D Dirac operators with singular potentials. It actually goes back quite a while into the late 80s, where Jussi Behrndt and also Dietrich Exner and Scheber have been treating the Dirac operator with such a singular potential on a ball, on a ball or on a sphere. And their computations, of course, can be performed by separation of variables. Then there was not much development in this direction until, now a few years ago, a series of papers from people from harmonic analysis and PDEs appeared. This is around Luis Vega and his former PhD and postdocs, Arrizabalaga and Albert Maas. So they published a series of papers on Dirac operators with this type of singular interactions on hypersurfaces. And that has led to quite a few publications in this direction. And well, it also inspired us actually to try, let's say, certain extension theory type methods to study Dirac operators with this type of singular interactions. So this is all for the 3D case. And now I would like to spend some time on the 2D case, where basically the results are kind of more complete, I would say. So this is a very recent paper. It has just appeared by the end of last year with Holzmann, Ourmieres-Bonafos, and Pankrashkin. So in the 2D case, the Dirac operator looks very similar as in the 3D case, actually. So we have the Pauli spin matrices here in the definition of the operator, and the free operator, so there's no potential here, is just minus I sigma times nabla f. So this is again sigma 1 partial derivative with respect to the first variable and the second. Plus a mass, which is assumed to be non-negative. Speed of light we set equal to 1. And similar as in the 3D case, one verifies by using the Fourier transform. This is a self-adjoint operator, and its spectrum is purely, absolutely continuous, purely essential spectrum consisting of these two half-lines. It's not semi-bounded from below. And this operator we wish to perturb now again by a singular type of perturbation. So here we again work with eta and tau. So instead of the beta matrix, we now have sigma 3. This is the proper replacement in the 2D case. And we have a delta distribution formally, which is supported on some hypersurface sigma. And here we use a pseudo-differential calculus, and that's why we have to assume here smoothness for the boundary, or here it's formulated sigma is a compact C infinity curve, which splits the plane in a bound domain omega plus and then smooth unbound domain omega minus. So the geometric situation is as before, except that we really require a C infinity smoothness here of this hypersurface, or this curve, this loop sigma. The definition of the operator is again very much similar as before. So this A eta tau, on each component, so inside omega plus and inside omega, or on omega plus and omega minus, it just acts like the free Dirac operator, and this whole delta type singular perturbation is encoded in the domain. And again, we have a transmission condition, which is just the proper replacement that we have seen in the 3D case, and it's given here. Okay, some comments on the condition. Well, I will go through this very quickly. In certain situations, this is not to be mixed with the critical case. This is -4, the critical case is +4. In certain situations, one can reformulate this transmission condition in the form of a true transmission condition, in a sense that the trace of F minus is a certain, by some matrix will be mapped into the trace of F plus. Whereas there is a decoupling, if eta squared minus tau squared is equal to -4, there is a decoupling in the sense that A eta tau actually is just the orthogonal sum of two self-adjoint Dirac operators acting on L2 omega plus or omega minus. And one just has, one could say this is a kind of Robin type condition for Dirac operators on domains. Such conditions can be found in the literature elsewhere. This is a paper of Ben-Gurion, co-authors that we mention here. And there appear similar type of conditions in other papers I have mentioned before. So I'm not going into further details here, but would like to spend now a minute or two for the spectral properties of these operators. And again, we have to distinguish, as in the 3D situation, in a non-critical and in a critical case. So in the non-critical case, one may say the results in a sense are not too surprising. So first of all, everything is made in the right way. So this A eta tau becomes in fact a self-adjoint operator with these transmission conditions. Because this is a compact loop or compact curve, there is a compactness property in the resolvent difference somewhere which ensures invariance of the essential spectrum. In the gap, just finitely many eigenvalues. And also the domain of this operator has some regularity properties. This is more technical issue maybe. But we remain here inside the Sobolev spaces H1 on the respective domains omega plus and omega minus. Now let's look at the critical case. So we have interactions strengths eta and tau such that eta squared minus tau squared is equal to 4. And in this critical case, again, one can ensure self-adjointness. And this is probably the main result of this talk, or the one I like most probably. In the critical case, without further assumptions on geometric properties of the loop or curve, there always appears essential spectrum in the gap. And there is one additional point, which is minus tau over eta times m. This can be adjusted. This can be an arbitrary point inside the gap that belongs to the essential spectrum of this operator in the critical case. Also, there is less regularity in the operator domain in this critical situation. So there is no Sobolev space regularity of positive order. And if one reduces or if one restricts the operator to H1, there is still essential self-adjointness. But the main issue here is the first item in this theorem. There appears a point in the essential spectrum in the gap. And some remarks on that. So first of all, one can play with tau and eta. And in this critical situation, one can always adjust tau and eta such that any point in this gap is hit by minus tau over eta times m. And instead of one loop, one could also consider finitely many C infinity loops. They should not kind of intersect. But if they are completely disjoint, one can in this way construct more points in the essential spectrum. So more loops give you more points that you can just adjust inside the essential spectrum as you wish. Okay, so in the critical case, maybe this is the main message of this talk, in the 3D as well as in the 2D situation, in the case that the interaction strength satisfies or is of certain critical nature, this is purely technical, the spectrum changes dramatically in the sense that there is essential spectrum in the gap. Thank you very much.
Very much. Some physical and some virtual clapping. So many thanks for the nice talk. So any questions for the speaker?
I've got one.
Yeah, go ahead.
Could we see the last slide again? I just, maybe I missed. So in the critical case, the first part says you have in the essential spectrum this point minus tau over eta times m. So is this independent of what the loop looks like?
Yes. So the loop is just assumed to be compact smooth. So it should split the plane in a smooth bounded domain and its exterior. But there is no further assumption on the geometry, on the shape of this curve. For each such curve, you have this particular point in the essential spectrum.
So is the multiplicity of this point equal to the number of loops then?
No. This is a
good... it's infinite, right? It's in the essential spectrum.
To be honest, we just know that it's a point in the essential spectrum. This is not necessarily an infinite dimensional eigenvalue. We do not have more precise knowledge on that. It could, you see, this point minus tau over eta times m, this could also be an accumulation point of discrete eigenvalues within the gap. So it may happen.
All right, okay.
So it may well be that it's an isolated infinite dimensional eigenvalue, but equally it could also be an accumulation point of discrete eigenvalues.
Sure.
We don't know.
Okay.
Okay, interesting. And this, so if I can ask one more thing, this about whether there's a physical meaning of this critical case. Yeah. This is complete speculation, but I wonder, you showed this, the Coulomb potential, and in that case, you also had a bound on the coupling strength, right?
Okay, well, this is physical.
And that's somehow related to the mass of the kernel of the atom, right?
Yes, I think if you allow all the physical constants,
okay.
Then it comes to the charge of the nucleon, which should be less or equal to 137.
Yeah, so I was just wondering whether something similar could be going on here.
Well, honestly, we don't know. For the moment, we do not have a physical interpretation of that. We can just see it in the proofs and, of course, in the results in the spectrum that a certain boundary integral operator, which appears here in a rather complicated form, it loses its compactness property. And yeah, this in the end displays in the spectrum, but we don't understand about the physics of that phenomenon so far.
It's interesting. Thank you.
More questions? Yeah.
May I ask something which is actually just following on this? So, I mean, if you have Dirac operator on just on the circle, say with a suitable boundary condition, local boundary condition, then you also find this point of essential spectrum, which you wouldn't expect. Of course, in this case, you would have just discrete spectrum otherwise, but you have one point of essential spectrum, and that has to do with basically surface state. So I mean, the corresponding solutions will be very closely localized to the rim of the circle. So do you have a similar thing here, that for this point of the essential spectrum, you would have corresponding solutions which are very closely localized near the boundary of omega?
That's an interesting question. I don't know, actually. We do not have well, no precise expressions, of course, but we do not have even qualitative properties of the corresponding solutions, or we have not been looking at. Maybe there's something to read off from the resolvent formula near that point, but I cannot give you an answer for that question. I'm sorry.
Yeah, but that might be help interpret this point of essential spectrum. If that was
that would make perfect sense. I agree. Yes.
Yeah, I think Matthias has a question.
Yeah. So you said you cannot treat variable coefficients. Do you have then a critical case there as well, or?
Yeah. Yes. Yeah. So we can treat variable conditions under certain weak assumptions. So we cannot allow eta and tau to be L infinity functions. They need to have a little bit of smoothness. And this critical condition, I think, in this situation would reduce to the functions being equal to +4 on a set of positive measure on that surface. So this is, it's basically the same condition.
Okay.
And of course, if they are bounded away from 4, this eta squared minus tau squared now as x-dependent function, then you would be non-critical.
More questions?
I have a question.
Sure.
You had this Krein type resolvent formula. Can you use it to maybe continue the resolvent analytically and then look at resonances, this kind of stuff?
That may well be, yes. Yes, that's very well possible. We have published a paper with Andrea Posilicano and Andrea Mantile on scattering properties of such type of Dirac operators. I did not mention that here at all, where exactly this is done. So, well, the basic idea is you consider, let's say, in the simple case here, the Klein type resolvent formula, the resolvent of the free Dirac operator you have well under control. And yeah, then you just need to study extension properties of these operators phi lambda star, and C lambda and its inverse. And then you can continue the whole resolvent over the continuous spectrum, so to say. Yes.
And what can you say about the resonances in this case? Can you compute them sort of explicitly for that, say for a delta potential on a sphere or something?
Oh, that may well be, yes. We haven't tried. Of course, for some solvable situation, I'm pretty sure this is doable, yes. But as far as I know, this has not been done.
But can you say that there are infinitely many, or some kind of qualitative statement?
Well, that would be no speculation. So I will not say anything. So we didn't do, but I'm pretty sure, of course, in the case of a sphere or a similar thing, one may well be able to go, of course, give more precise results on that. It may even be that Mantile and Posilicano went on in this direction and they computed some models, but I have not seen the most recent results.
Okay. And I have another question. If I remember correctly, if you look at the Dirac operator in one dimension, it's just the delta interaction at one point, then you have these issues with, you know, if you want to approximate the delta potential by a sequence of functions, then the coupling constant undergoes some strange kind of renormalization. Is that something that happens here as well?
Actually, this is still a kind of open problem to let's say, to justify the, oh, no, I went too far, sorry. I went too far again, sorry. So it's kind of an open problem, actually, to justify this step here. I think the best result I have seen is very recent. There is a paper in the archive by Exner, Lotoreichik, Albert Maas, and maybe a fourth author, I'm not so sure. And I think they prove in the 2D situation at least some strong result. But what is in at the moment missing? For Schrodinger, of course, this has been done and treated in very much detail to prove actually resolvent convergence in the operator norm for a sequence of locally scaled potentials which you squeeze and they converge to delta in a suitable sense. For I think with an additional smallness condition, if the eta here and also I think if the eta is very small and there's no tau, I think then there is a result by Ourmieres-Bonafos and maybe Pizzicillo. They published it 2 or 3 years ago, where they prove under very strong additional assumptions, at least there they prove, and if I remember right, this is actually a convergence in the operator norm. Okay. And this is something we have on our agenda to justify this approximation. Mm-hmm. This is there are some open problems, yes.
Okay, thank you.
So any more questions?
I would like to ask something.
Yeah.
So in the 3D case, you had this example where the essential spectrum picks up a flat piece of the hypersurface. So there, the geometry of the hypersurface actually contributes to the spectrum. But now in the 2D case, you said that your essential spectrum value there is constant independent of the curve. Yeah. Is there what is going on there? I didn't know.
You see, in the 3D case, we do not have a full understanding of this effect so far. In the 3D case, we are able to prove under additional geometric assumptions on the hypersurface that there is essential spectrum. We believe that this is this is not the best possible result. So I guess also in the 3D case, essential spectrum in the critical situation is some properties that should arise as long as this hypersurface has just some modest properties, let's say.
Okay.
But we do not have a complete result. Whereas this is the advantage in the 2D situation. There we have it, at least under a smoothness assumption on the curve.
So it still could be the same behavior.
Yeah. Well, I would guess yes,
Yeah.
but I have no idea how to prove it.
Okay, thanks.
All right, so I would suggest we thank the speaker again and postpone further questions to the informal chat. So thank you very much.
It's a pleasure to speak in Cardiff virtually.